Okay, let's dive right into this explainer and uncover how scientists ingeniously use the physical properties of light as an invisible ruler to measure gases we literally cannot even see. Now, it sounds like absolute magic, right? But it's actually just brilliant engineering and physics coming together. Today, we're exploring a truly remarkable device from the world of optics that does exactly this. To start things off, we need to talk about light's dual personality. While we know it can act like a particle, which we see in things like the photoelectric effect or black body radiation, we're going to focus entirely on its wave nature today. Specifically, we're looking at the phenomenon of interference. That's where intersecting light waves overlap with each other to create highly measurable patterns. Section 1. Enter the interferometer. Harnessing interference. Early physicists were incredibly clever. They figured out how to harness this specific wave behavior to build incredibly precise tools. An interferometer, like the renowned refractometers designed by Jamin and Rayleigh, basically takes these intersecting light waves and uses them to calculate the refractive index of a gas. You can think of it as a translator, turning the behavior of light waves into readable data about something completely invisible. Section 2. Inside Jamin's refractometer, the mechanical breakdown. Let's look at the actual blueprint. The absolute foundation of this device relies on two glass blocks, which we'll call M1 and M2. Now, these aren't just any random pieces of glass. They have to be cut from the exact same block to ensure they are perfectly identical. They're silvered on their back surfaces, so they act like mirrors, and they must be arranged perfectly parallel to each other. This exact precision is totally non-negotiable. We have to ensure the light paths remain completely identical throughout the whole experiment. So here's how the sequence actually plays out. Step 1, monochromatic light hits block M1 at a precise 45-degree angle. Step 2, the block splits this light into two parallel rays. Step 3, these rays pass through two entirely separate, identical evacuated tubes. And finally, step 4, the beams recombine at block M2 to form visual interference fringes. Think of these split beams like identical runners on a racetrack, traveling completely unhindered through their own separate tubes before crossing the finish line at M2 at the exact same time. Now here is where it gets really cool. The crucial point is that when we slowly add a mystery gas into just one of those tubes, it acts like a physical headwind. It actually slows that specific light runner down. This increases the optical path of that beam, which physically shifts those visual finish line fringes we see in the telescope. And naturally, the more gas that enters and builds up pressure, the more the fringes move across the telescope's crosswire. Which brings us to the math. By counting the exact number of those shifting fringes, which we represent with the letter N, we can calculate the refractive index, or mu, of the gas in the tube. The formula is actually quite simple, but profoundly useful. Mu minus 1, multiplied by the length of the tube, L, equals the number of fringes, N, times the wavelength of the light, lambda. But we hit a massive practical roadblock here. What if the gas creates way too many fringes to count manually? Imagine trying to count moving, microscopic fringes across a telescope crosswire by eye. It's a massive, tedious headache for scientists, right? If you blank and lose count, the entire experiment is ruined. So, this poses a huge problem for both efficiency and accuracy. Section 3, the compensator upgrade, solving the fringe counting problem. To entirely bypass that manual counting nightmare, Jamin introduced an ingenious fix called a compensator. It's basically two equally thick glass plates, C1 and C2, cut from the exact same piece of glass. They're inclined at a small angle and rotated together on a horizontal axis using a divided dial. By placing one of these plates in the path of each beam, rotating the dial introduces a highly controllable, easily measurable phase difference. Let's contrast these two methods real quick. In the old method, you're staring through a telescope using monochromatic light, manually counting endless shifting lines. But with the compensator method, scientists swap to white light, which conveniently produces a very distinct central achromatic fringe. When the gas shifts the fringes, they don't count them anymore. Instead, they just rotate that calibrated dial to realign the central fringe back to the crosswire. Once it's aligned, they simply read the optical path difference directly off the scale. It is an incredibly elegant leap in experimental design. Section 4, putting it to the test, running the numbers on example 3.1. Okay, let's see this in action. Let's say we set up our Jamin's refractometer. We've got our two evacuated tubes, each with a length of 20 centimeters. We emit our gas slowly at a specific temperature and pressure, and we observe exactly 100 fringes cross the field of view. The wavelength of light we're using is 5460 times 10 to the negative 8th centimeters. With our setup complete, we now have all our known variables cleanly established. Plugging these precise measurements right into our established formula reveals just how powerful this mathematical and physical setup truly is. We just rearrange our earlier formula to solve for mu, the refractive index. So it's 1 plus the result of our fringes times our wavelength divided by the length of the tube. We are essentially translating physical lengths and light waves into the hidden intrinsic properties of a gas. And when you actually run those numbers, the result is incredibly precise. We discover the refractive index of the gas is exactly 1.000273. Just think about that. We just measured a property of an incompletely invisible gas out to the millionth decimal place, using absolutely nothing but strategically placed glass blocks, evacuated tubes, and light waves acting as our invisible ruler. This level of sheer ingenuity is exactly what makes optics so fascinating. And honestly, it leaves you wondering, if we could achieve this astounding level of measurement using basic optical engineering and the interference patterns of light, what invisible forces are we on the verge of measuring next with today's technology? Thank you for exploring this brilliant piece of scientific history with me today.